One of the more mysterious error messages you can get in GHC is that a type variable is ambiguous. And one situation where this occurs rather frequently is if type families are involved. And often GHC actually additionally points out that you are using a type family and the type family is not injective. So in this episode, we're going to discuss what injectivity actually means and how it interacts with GHC's type system and inference algorithm, and what you can do in a situation like the one I just mentioned, where you get such a complaint from GHC.
Right, so welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, this show is live streamed, and we would like to invite you to submit questions and comments in the chat. If you do, we will try to show them on screen and discuss them.
Okay, so let's start with the definition of injectivity. So injectivity is a property of a function. So at first, it doesn't seem to have anything to do with types. A function f is called injective if for all x and y, if we have that f of x is equal to f of y, if that implies that x is equal to y. So as always, it's easiest if we just look at an example of an injective function. So let's consider the function double from integers to integers. And double is simply doubling the integer. And double is injective because if I tell you that, for example, double x is equal to 8, then there is exactly one option for x, right? So x must be equal to 4. And that is essentially what this definition of injectivity means, because it says that if you have a double y that also is equal to 8, then x must be equal to y, so y must also be 4. So it basically says if you have a result of a function, there must be a unique argument. It does not say that for any result in this result type, you must have a source. So there are like other integers like 9 that do not even appear in the image. But if there is a function argument that produces a result, then it must be unique. And let's also look at an example of a function that is not injective. So if we consider even from integer to bool, I'm not going to define that because that's already in the prelude. But if I'm now going to tell you that we know that even x is equal to true, for example, then now there is not just one choice for x, but there are actually infinitely many, right? So we can choose x equals 4, we can choose x equals 0, x equals -4, x equals 42, and so on, many, many more. So, so there is no way to conclude from the result of the function to the argument of the function.
Yeah, so intuitively, injective simply means if you know the output, then you can also figure out what the input must have been.
Right. So now we are interested in injectivity for Haskell types. And for that, it is interesting to look at functions on the type level. So not functions as Haskell types, like not functions of type A to B or something, but functions that take types to other types. And actually, we've already mentioned type families in the introduction, so those obviously qualify. But even before type families even were in Haskell, Haskell had always parameterized data types, such as maybe or lists. And you can see such parameterized data types as functions on types, because for every input type, there is a maybe type, for example, right? If I give you int, you give me maybe int. If I give you bool, you give me maybe bool. You can apply maybe to any type. But it is a strange function because it does not really compute. The result of applying maybe to bool, right, is simply written as maybe bool. And there is no reduction, no computation. But this is interesting from the perspective of injectivity, because it means that parameterized data types are trivially, by construction, injective. We can simply read off the argument from the result. Right? If I see a result type, such as maybe bool, I know immediately that the argument must have been bool. And the same holds for lists, and the same holds for pairs or ithers, which even have multiple arguments. We can always read off all the arguments from the results. And I want to briefly mention one other example because it will come back later, and that is proxy. So if we have a data type that is defined like this, data proxy A equals proxy, then then it is a bit like the unit type in that basically there's only one value of this type that is like one total value of this type, which is called proxy. And it doesn't really depend on the argument A, right? But nevertheless, in Haskell, a proxy int is different from a proxy bool. Right? By definition, these are treated differently, even though in principle they have the same inhabitants. So like you could take the perspective that you should be able to switch between them safely, but in Haskell by design, this is not the case. So data types in Haskell are always injective.
Yeah, so the right-hand side of a data type definition, like the constructors, the arguments to the constructors, anything at the value level is completely irrelevant here. We just care about the type level information.
Exactly, yes. Okay. Now let's look at like how injectivity becomes relevant for type inference and how we get these ambiguity errors and so on and so forth. So let's actually provoke an ambiguity error right now by combining two functions that are both overloaded. That is one like other way next to type families that often provokes these kind of ambiguity errors. And let's use show, which we all know. I mean, it takes an A to a string as long as A is in the show class. And let's take empty, which is from the monoid class and simply produces the neutral element of that monoid. And it's just a way to conjure up an A, a more or less arbitrary A, and it's constrained by the monoid class. And then show can consume such an A and turn it into a string. And if we apply show to empty, right, we should be getting a string, right, because we're feeding something of a flexible type into this function which expects something. But there is still a show A and a monoid A constraint. We don't really know like which monoid to choose. There is no contextual information here that tells us which monoid to choose. And in fact, if we try this, right, if we try example equals show empty here, we get an ambiguous type variable error that complains about exactly this. That says there is no information here to conclude which monoid I should be choosing, and therefore also nothing to conclude which show instance I should be using. But we can simply fix this by providing a type annotation. So I can say, I want the list of booleans monoid, for example, and then all of a sudden this works, and I can actually show this, like call this perhaps more meaningfully show empty. and this is of type string, and if I execute this, I do get a string representing the empty list. Okay, so far so good. Now I can like make this a little bit trickier by saying I want to abstract from this monoid, and I want instead to have the monoid be specified by an extra argument. So I want to take an argument here, some x, and I want to turn this into a function that takes some a, and then uses this monoid, uses like show a and monoid a on this a in order to produce a string. So we want to get this a here to be used as the as a type of empty here. And this is a bit tricky, right? Because now there is no connection between this x and this type. So, and even if I write a here in normal Haskell syntax, this a here does not have anything to do with the a and the type signature. But there is a language extension called scope type variables, which is enabled by default in recent GHCs and like all the GHCs that support GHC 2021. And if you write an explicit quantifier, then the a and the type annotation here means the same a as here. And now it works, right? Because we don't even need the x. We simply use the argument here to determine which monoid we want to choose. So for example, if I reload and then call show empty on the list false true, then this now determines that I'm using the list of booleans monoid, and I get the same result as before.
Yeah, so this argument is completely unused, right? We're just using the argument to determine, to give some information to the type checker here.
Right. And now we can get yet one step further and change this A here to maybe A. And now it still works. I mean, obviously, if I call this function, I now have to say something like just or false true. But the interesting thing is the type propagation is still fine because maybe is injective. And this is really essential now, because we are now, we have to determine what A is, but from looking at the call, we only know what the argument type is. We know that the argument type is a maybe list of Boolean, but because from the fact that the argument is a maybe list of Boolean, we also know the argument to maybe and know that, okay, so the A must have been a list of Booleans. We know which monoid we have to use and which monoid we have to show. And therefore, this particular call works. Right? And in a situation such as if I pass nothing, now suddenly I don't have that contextual information immediately available anymore. If I would try to make a call like this, I would actually get an error message, right? Again, about an ambiguous type variable arising from the call of showEmpty. But now I can still give a type annotation and make it work. And go back to the previous.
But the thing here is that it doesn't matter at runtime whether this is just or nothing, because again, we're not looking at it. The problem is only that if we specify nothing, then nothing has many types.
Yeah.
Right? And so the type checker does not have enough information now to distinguish which one do you mean.
Mm-hmm. Okay. So now we've seen how sort of the injectivity of parameterized data types can sometimes help the type checker along. And now we can also see, perhaps already predict, how this can fail in situations where we're no longer necessarily injective. And this is where type families come into play. So if we now consider a type family, which I'm just going to call fam for family here for short, which takes types to types. So this is like a function on types. And I mean, type families come in different flavors, open and closed. This is an open type family. So far, I haven't actually defined any particular mappings of types, but I can define mappings of types. So I can do something like type instance fam of list of bool equals bool, for example. And now this is fam is a type family that if it's applied to list of bool, then it reduces to bool, to a plain bool. And if it's applied to anything else, then it doesn't reduce, then it's stuck, as it's called, right? But that doesn't really matter here.
So now we really are doing computation at the type level.
Yeah, exactly. And now we could try the same thing as here again, only that we replace maybe with fam. Right? So basically we're trying to do exactly the same thing, but we are replacing maybe with fam. And this is where things go wrong. And so here we get one of these famous type errors, right? Couldn't match type fam A0 with fam A. Expected fam A to string, actual fam A0 to string. It looks like it's the thing that is being expected. Nevertheless, it's not accepted. And we get this remark here, fam is a non-injective type family. Type variable A0 is ambiguous. And it actually tells us, oh, well, perhaps to defer the ambiguity check, enable AllowAmbiguousTypes and all will be well. So that's actually something we can try, but we can also already discuss why this is a problem, right? Because we already know, we've already discussed this now. So here it was crucial to know that we can conclude the choice of A from maybe A. There is no other way to go. And for type families, we generally can't. And GHC is pessimistic here, right? So even though in this particular case, if you look at the type family, it is actually injective because there is only a single mapping. So for the result bool, there is only a single source type. Nothing would prevent us, in particular because this is an open type family, to go somewhere else and define another type instance and map something else to bool. So for example, there are other monoids in the base library, and one is called all. We could also add this instance later somewhere else, and then the type family isn't injective. And because this can happen, right, GHC will just pessimistically assume that type families are not injective and will not conclude A from an application of fam of A, because here, by knowing that fam of A is bool, we simply don't know what A was, right? There are multiple possible choices for it. Now, as it suggests this allow ambiguous type. So let's see what happens if we do this. Let's actually allow ambiguous types. And indeed, suddenly the error message goes away, so everything looks fine. So now we have a working definition, but we can't use it, actually. If we try to use this as before, and I can actually give an example in here. If we try to do something as before where we say show empty prime now, and now what would we actually want to apply? Well, a Boolean, right? Because we have to apply a fam of A. So like say true, right? Or false. But in both cases, we get an error message again because GHC cannot unify fam of something with Boolean. It cannot determine. I mean, it would also actually even be difficult. It has to kind of scan the entire definition of the family, see whether anything maps to Boolean, but then even then there may be multiple choices right here. And so it doesn't do that. And perhaps even more infuriatingly, we cannot just give an annotation here either. We cannot say that we mean that this is fam of list of bool, because this is the wrong way to provide this information. As far as GHC is concerned, fam of list of bool just reduces to bool.
Can you show the type error here?
Yeah, it'll.
But this used to drive me crazy, right? Like it's expecting fam of A and it's just fam of list of bool. It should be obvious, right? Like it's right there.
Yeah. But I mean, as far as GHC is concerned, this is exactly the same as if I had been writing bool here, right? And it is still not meaningful. It is not telling us really what the A should be instantiated to, because there could be multiple things. And it doesn't.
Sorry, go on.
And it doesn't matter whether we have the second clause here or not, right? The actual implementation, we don't even need any of these. I mean, the errors don't really depend on that. GHC will just always assume that type families are not injective. Okay.
Yeah, so when you write true of type f of list of bool, it's important just to, again, this is real computation, right? That computes, that evaluates to just being bool. So if you write true of type fam of list of bool, that's just a complicated way of writing true of type bool. You're not actually giving any more information. Exactly,
yeah. So, okay, now we've I think analyze the problem. Now let's talk a little bit about what kind of avenues we have for working around it or fixing it. So perhaps the easiest way to make this work now is to actually explicitly say how we want to instantiate the A. And that is something that these days you can relatively easily do in GHC by enabling another language extension, which is called type applications. And if you have type applications, you can simply, like if you have a quantified variable, you can use a special syntax with an at, which basically says like we want to instantiate this polymorphic function at this type, and then you can provide the type we want to instantiate show empty prime as, and we can say like what choice of A we want to make. So for example, we can say we want this to be instantiated at list of bool, and then this argument must be a bool. I mean, whether we annotate it or not is now irrelevant, right? And if we execute example, we get our old like string representing the empty list back. But we can also use the other one here now. Like we can also say we want to instantiate it to all, and then the example would evaluate to the neutral element of the all monoid, which happens to be true as well. There's nothing to do that with the fact that I've passed through here, like if I pass false, I would again get the true element, because again, the value here is actually not used. We're only using this for the type information that is attached to it. Okay, so that's one option, right? If you are in such a situation, you can use an explicit type annotation. Another very related option is to use the proxy type that I mentioned before, because the proxy type carries no information on its own except for the type checker. The only purpose of passing a value of proxy type is to pass some information to the type checker. And if we add an extra argument of type proxy A to this show empty function, then of course I also have to add an extra unused argument here. Then we can instantiate here by using a normal type annotation again, proxy of type proxy list of bool, for example. And now I can do the same thing as before with the type application by just passing a proxy of the right type. I could also use a type application here for instantiating the proxy to the right type. Now this looks almost the same, only slightly more complicated than before. Nevertheless, I prefer it. Why do I prefer it? Well, because now you can actually disable AllowAmbiguousTypes again. And that's actually a good thing, right? Because if you compare these two type signatures, and if you ignore the proxy for the time being again, right, without the proxy, then they look pretty much the same optically. They have some capitalized thing applied to a arrow string and some class constraints. And as a reader, it's not always easy to know, right, is this a problematic type signature, yes or no? Because it really depends on whether these things that look superficially the same, whether they are injective parameterized data types or whether they are potentially non-injective type families. And that makes a huge difference. Right. And it's not so easy to tell just by looking at it. Also by looking at some library documentation from some module that you might be using. If you just look at it, it's not so obvious to tell, does this need extra information, yes or no? And so it's good in general to get this warning, right? It's good to not just allow ambiguous types everywhere. And it's also, even if you, for whatever reason, want to enable it, it's still also a good hint to the user that, here you are expected to give extra type information, right? Whereas otherwise it's not so obvious, if you have a type that is quantified over many different things, right? Actually, there was a good example in that Etzko showed in the last episode, in episode 2 of the Haskell Unfolder. Etzko had this encryption class. Let me see if I can reproduce that. So it looked something like this: encryption E where type key of E. So that was a type family, an associated type, and a class is more or less the same as a type family. So you had an encryption mechanism E, and there was a key type associated with it, and a type of encrypted values associated within it. And then there was an encrypt function, which was of type key E to A to enc EA, right? And now if you look at this, right, you see that there are two type variables here, E and A. And the A is fine, actually, because the A appears as a bare type argument here as well as an argument to the enc type family, right? And actually also the enc type family is not even is type to type, but let's we could also make it yet more complicated and write it like this, but then I think I'm not sure. No, I'm getting derailed. Let's just keep it as it is. But anyway, right? Regardless of how enc is exactly defined, I mean, the A would always be fine because it appears here. That's the point. Whereas E is not fine. E appears only as arguments to type families, and therefore we're getting this ambiguity error again, and key being a non-injective type family. And that's why it's a good idea to put a proxy here, right? And again, that makes it clear.
Yeah, so I mean, to me, this is a much better solution than allow ambiguous types, right? Like, I mean, I understand it already, but the signature now makes it very clear which type variables are problematic and which ones are not. And if you have many type variables, and often you do, there's typically only one or maybe two that are problematic. And if you just have a proxy, you just immediately clear to the caller, okay, I have to be careful about this. I have to make a choice here. The rest will be fine.
Yeah. Okay, and another thing to perhaps re-emphasize at this point is also that even if you're never planning to write your own type families, right, if this is all sort of like a level of Haskell that you're typically not using, it's enough to run into these kinds of problems if you're using a library yourself that makes use of type families. And quite a lot of libraries make use of type families at some point, right? Because you're then working with functions that involve type families, you're combining them in new ways, and sooner or later you might end up in a situation where a type variable that you quantify over appears only as the argument to a type family, and there you go, right? Then you need like a proxy or an explicit type application, but better a proxy, right? So this is something that can happen to you even just as a user. But okay, so let's nevertheless also discuss like one or two other options that you might have, in particular also if you're perhaps the library author, if you're designing the type family in the first place. So if you're designing the type family in the first place, and if you are in the rare situation, I think it is actually a rare situation, that the type family really is injective, right? Then there is an extension in Haskell that is called type family dependencies, which allows you to actually declare the type family to be injective. So let's perhaps, well, I mean, I can try to do it with fam itself. Sorry, I did not mean to remove this. So the syntax for this is a bit weird. So you're saying like, okay, you give a name to the result, R, and then you say the result determines the input. But this is effectively what injectivity says, right? The result determines the input. If you know the result, you should also know the input. And now GHC correctly complains about my second type instance here because it already violates the injectivity annotation that I've just given, because it also maps to bool and the first one already maps to bool, so it's complaining about this. So that's like, if you like, good, because it means that these injectivity annotations work. But it's also, it shows perhaps how critical it is, because in practice many type families simply aren't injective. There are quite a few that aren't. But if you do this, right? If you do this, you can actually get away with without the proxy. So we could like write yet another version of show empty just for the sake of demonstrating this for the time being, without the proxy argument again. And this goes through now. And if I duplicate the example to use show empty double prime, also without the proxy now, this also goes through now. Right? So this now works. Now GHC is actually looking and seeing that bool is a valid value to use here, and that it obviously must correspond to the choice of list of bool.
Yeah, so it's interesting what's happening here, right? You're giving a Boolean value. GHC needs to figure out what A is. So it kind of needs to compute an inverse, right? It needs to see which inputs to this type family would give me bool. And we need to scan through all your definitions, like computing an inverse, and oh, it must have been list of bool.
Right, and that is actually the other option that I wanted to briefly mention that is also sometimes interesting. You can define your own inverse. So rather than...
Andres, there's one question that I think we might just discuss at this point.
Yeah, okay.
And so Fender asks, can we add functional dependencies to associated types in type classes?
Can we add functional dependencies to associated types and type classes? So functional dependencies are, I mean, I'm assuming you mean these. I'm assuming you mean these because yeah. I mean, like functional dependencies are attached to type classes, but these look pretty much like functional dependencies, and they're called type class dependencies. And yes, so if a type family is associated, like here, you could still use that syntax. You could use something like r arrow sorry, bar R determines E here. Sorry, probably not with the colon type written
you
like
can.
this.
You just need to press
yeah,
it.
but you have to probably put it in.
Yes.
Oh no, this is also wrong. You have to put it here, right? I guess. Yeah.
Oh yeah.
It's still not accepting this. Perhaps you need parentheses as well.
Yes, you do.
Yeah. Okay. But yeah, but that's possible. I mean.
And a related question from Mikolai: what about closed type families? Can GHC deduce on its own if they are injective or not?
So I think GHC could, but GHC doesn't. So the I think the design decision for these type family dependencies is that you want to annotate it. It's a property that, as I said, I mean, like many type families aren't injective. So if you are deciding that you want a particular type family to be injective and you want to rely on this, it makes sense to make it explicit and not to rely on inference and sort of suddenly break it by. Because even for closed type families, you might go back at some point and change the definition or add a new clause. And if you're relying on it to be injective without declaring it that way, like your programs could break at a completely different place. So I think that it makes sense that GHC does not infer it, even though it potentially could. Yeah. Okay, so we're already a little bit over time. So perhaps I'm not going to actually explain this in a large amount of detail anymore, just sort of as a sort of final pointer. And also in the repository, I will add an example for this. Like we have this GitHub repository with accompanying materials. So a thing that sometimes is helpful to know is that instead of using such an injectivity annotation, you can also define an inverse yourself. Like you can go and define like an inverse family, which basically goes the other way around. Don't do the annotation here, and do something like type instance fam inf of bool equals list of bool. So this is just mapping from bool back to list of bool. And then say here that A must be equal to the inverse of the family application of A. And once I give this strange equality constraint here, you see all the type errors disappear, and it actually works. And the real interesting thing is that now I could even uncomment this line here and it would still work. So it can work in a situation where the family is not actually injective. So, and this isn't a real inverse, it's sort of a partial inverse mapping something back to some sort of a canonical representative. So that's one of the reasons why it can be interesting. There are other reasons why it can be interesting. It's simply more flexible in general than the current type family dependencies declaration. There are situations where you, for example, have the result and one argument determine another argument. And that is currently not expressible with type family dependencies as they're implemented. And it also sometimes can just be a good idea to have a name for the inverse that you can use in your code. But in this case, you have to manually define it. So what would be really nice, in my opinion, is if the type family dependencies would like basically as a witness of what they're doing, would basically define the inverse in such a way for you that you could also use it and invoke it. But currently, that is not the case. Yeah. Okay. I think I could tell much more, but I think we're at the end of time.
Yeah,
so if there are no more questions,
no, I don't think so.
Then we should probably conclude at this point.
Yeah, so thanks everybody for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe, and feel free to leave any further comments below. And yeah, we'll hope to see you all in just over 2 weeks. Bye everyone.
Okay, what's the next topic?
I'm going to be talking about my new testing library called Falsify. So
okay.
Yeah.
All right. Bye.